Welcome to Chapter 4, Applications of Differentiation. We're going to be following the slides from Stewart and his calculus text, Early Transcendentals, 8th edition. We're looking at Section 4, Indeterminate Forms and L'Hopital's rule. And the first thing we're going to look at is a function f of x equaling natural log of x over x minus 1. And if we wanted to try to look at the behavior of this function, even though the function's not defined when x equals 1, and I should say that in this video I will do what I typically do, which is march through and comment on and explain some of these, if not all of these slides that are provided by the author. And then at the end, I will switch over to a notepad and I will work out a couple of example problems that very closely pertain to what it is that we're talking about in these slides. So without further ado, let's keep examining these. So even though the function's not defined at x equals 1, we want to look at the behavior near an x value of 1. And one way that we could articulate that is to say that we want to look at the limit as x approaches 1. And as we know, the limit from the left needs to equal the limit from the right in order for us to say that this limit actually has some defined value. So that's a great way to look at it near 1. So we're going to look at it from both sides. In computing the limit, we can't apply law number 5 of limits because the limit of the denominator is 0. In equation number 1, it's particularly unique because not only is the denominator 0 or approaching 0, but so is the numerator. And when you have a function or you're evaluating a limit of this kind of a rational form where both the numerator and the denominator are tending towards 0, we refer to that as an indeterminate form of type 0 over 0. So that's what we're talking about, but what are we going to do about it? Well, sometimes you have the opportunity when working with a rational function like this one to factor both the numerator and denominator, canceling out a couple of the factors and leaving yourself with a denominator here of x plus 1, which is nice because with an x value approaching positive 1, we can do direct substitution into the numerator and, most importantly, maybe the denominator, and evaluate the limit, which turns out to be 1/2. We couldn't do that without eliminating this factor of x minus 1 from the numerator and denominator, because at its outset, direct substitution of the number 1 would result in a numerator and denominator of 0. So that's one way to eliminate, or to evaluate, a limit where your numerator and denominator are both trending towards 0. Here is another instance of that, and how did we go about solving or evaluating this limit? We used a geometric argument to decide that that limit is equal to 1, or to prove that it's equal to 1. But those two methods don't work in all scenarios. And what you're looking at here is one of those scenarios. So we're not going to examine this geometrically. We're not going to be able to reduce or cancel anything out or simplify. And here, notice that our limit is taking x values toward positive infinity. And what we end up with is a numerator and denominator that are both trending toward positive infinity, which is another indeterminate form of type infinity divided by infinity, or if you had negative infinity in the denominator or negative infinity in the numerator, you're still looking at a problem. A big problem, maybe a problem that you're not familiar with or haven't ever seen before or don't know how to solve. So just as a reminder, a limit trending toward infinity of this form could be evaluated without using what we're going to be talking about, L'Hopital's rule. This limit could be evaluated by doing a bit of a trick and dividing both the numerator and denominator by x squared, which is the variable to the highest power occurring in the denominator. So x squared is the largest exponent in the denominator. So we're dividing all terms, this one and this one and this one and this one, by x squared, which results in this equation. This equation we can evaluate by sort of direct substitution. The infinity appearing squared in the denominator here takes that fraction to 0. This is the same fraction going to 0, so we can simmer this down to a value of 1/2. This method does not work for limits such as what we saw in this equation. So not all of these strategies can be applied all of the time. And so, for the less familiar cases, perhaps we have L'Hopital's rule, which can be applied under certain circumstances, the 0 divided by 0 set of circumstances, or the indeterminate form where we had positives and or negative infinities involved in the numerator and denominator. So this is, for the most part, how we're referring to the two indeterminate forms. I think we could safely put a plus or minus in front of that fraction because the infinities could go opposing directions. So if the limit on the right side exists, right, so we've got these two scenarios that I circled up here, this one and not that one. That one and then, come on now. Oh, heck. I'll show you. When we have either of these two scenarios and we're evaluating a limit with those functions as the numerator and denominator, we can evaluate it by applying the same limit, but applying the limit to the derivative of the numerator and denominator. We can only do that if the limit on the right-hand side exists. So, instead of trying to talk about it in a format where there are no numbers, let's keep pressing forward so that we can look at some actual examples. L'Hopital's rule says that the limit of a quotient of functions I like circling things while I'm talking so that you're not just staring at a blank screen. Plus, it keeps me entertained. I don't want to use that color. How about this one? L'Hopital's rule says the limit of a quotient of functions which is here, there is the limit of our quotient of functions, is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. We have to be working with one of these two formats, which results in one of these two indeterminate forms, and the limit on the right side has to exist. It is especially important to verify the conditions regarding the limits of f and g before using L'Hopital's rule. Noted. And it's also valid for one-sided limits and for limits at infinity or negative infinity. So our limits can look like any of those four, in addition to simply stating the limit as x approaches a. And a third note is that there are, or for the special case, in which f of a and g of a are both equal to 0, so the numerator and denominator must both be equal to 0 when x is equal to a. That's the special case that we're operating in here. And f prime and g prime are continuous, and the derivative of the denominator evaluated at a does not equal 0, because that wouldn't be good. It's easy to see why L'Hopital's rule is true, using the alternative form of the definition of a derivative. Derivative over derivative, limit of that same quotient as x approaches a. So you'll see that the a's are appearing on the right. Here they were just x's, like we have done direct substitution. And we can take and turn that into this alternate form where we're taking the limit of the numerator and limit of the denominator. But look at how the derivative is being presented. There is f prime, g prime, and then from here it's just algebra. That's just a copy and paste onto the next page. Just double checking. It's strange that they are identical. Onto the next slide. And then as we go from here down to here, we have performed a keep change flip. So we multiplied by the reciprocal of the denominator. Oops, multiplication dot appeared there. And x minus a over g of x minus g of a. And the x minus a is canceled, and we're left with f of x minus f of a over g of x minus g of a. That's what we're seeing here. And then we go from here over to here, and the f of a and the g of a disappear. Where did they go? We were told that this was a very special case, where f of a and g of a were both equal to 0. F of a is 0, g of a is 0, therefore they have disappeared, leaving us just with f of x over g of x. You're very excited right now. It's just thrilling that we've discovered that. What is it that we just discovered? The limit as x approaches a of f of x over g of x equals the limit as x approaches a of the derivative of x over the derivative of g. See the prime symbols there? Don't see the prime symbols in here. So in the very specific case where f of a and g of a both equal 0, it's very easy to see how L'Hopital's rule is derived. The limit of the quotient of the derivatives equaling the limit of the quotient of the original functions. When you've got something other than 0 over 0, considerably more tricky to perform the proof. Now an example, finally. Find the limit as x approaches 1 of the natural log of x over x minus 1. What's the strategy here? Well, first let's confirm that we're in the correct environment to even be applying L'Hopital's rule. And the limit of the numerator as x approaches 1 is equal to 0. The limit as x approaches 1 of the denominator is equal to 0. Therefore, the limit is an indeterminate form of type 0 over 0. Okay, so we can apply L'Hopital's rule. Let's take the limit of the numerator and the limit of the denominator. Sorry, let's take the limit of the derivative of the numerator and the limit of the derivative of the denominator. What is the derivative of the natural log of x? Well, it's 1 over x. And what is the derivative of x minus 1? Well, it's 1. So 1 over x divided by 1 is the same thing as 1 over x, and we're evaluating this limit as x approaches 1. Can we perform direct substitution now? We absolutely can. We get 1 over 1, which is equal to 1. And so we have evaluated the limit of this quotient, which initially was in an indeterminate form of 0 over 0. I'm so proud of you guys. You did it. Now let's talk about indeterminate products. So this is going to be weird but not weird. And you'll see why. It'll accumulate. We're still looking at two functions. We've got the limit as we've got the limit as x approaches a of a function f, it's equaling 0. But here, as x approaches a, the limit applied to the function g is equal to infinity, or it could equal negative infinity. And we're taking the limit as x approaches a of the product of those two functions. And this bit about the struggle is cute. You can read that on your own. This is called an indeterminate form of the type 0 times infinity or 0 times negative infinity, and we can deal with it in a clever way, and that is to say that we change the product f times g into f divided by the reciprocal of g. Or, if it were more convenient, we could take the product, leave g in the numerator, and divide by the reciprocal of the function f in this case. Why are we doing this? But this seems a little bit strange, because remember, the limit of f of x as x approaches a was going to 0, and for g it was going to infinity. Fg, 0, infinity. This now says 0, and this says 1 divided by infinity. So again, this was 0, and this is 1 divided by infinity. What is 1 divided by infinity? It's 0. Doesn't that mean then that this is 0 divided by 0? It sure does. And don't we already know how to deal with that? We sure do. It's L'Hopital's rule. We've just been talking about it. All right, smarty pants. So what's going on over here? What's up with this one? Well, remember that g, the limit as x approaches a, the function g was going toward infinity. And f was going to 0, which means this is 1 divided by 0. And what does that equal? But infinity. Doesn't that mean that what's really happening here is that we've got infinity divided by infinity? Sure does. And don't we know how to deal with that? L'Hopital's rule. Fantastic. So we're taking a slightly different looking problem and converting it into a problem, a type of problem, a type of issue like 0 divided by 0 or infinity divided by infinity, but we already know how to deal with that. So it's clever in that way. It's also weird in that way, but it works. Example 6. Here we're approaching 0 from the right. That's the little plus sign. And if we look at this as a product by direct substitution, this would be a 0, and this is the natural log of 0. Well, e to what power would equal 0? The answer is that question mark would have to be negative infinity. So what we have here is the product of 0 times negative infinity, which is an indeterminate product. 0 times infinity or negative infinity. There it is. All right, so we're in the right environment. Now all we have to do is convert this thing over so it fits more into the traditional L'Hopital's rule kind of a situation. And then we'll know how to proceed from there. Here's our solution process. We're going to write the value x as 1 over 1 over x. Okay, I'm interested to see where this goes. The good news is that 1 over x heads toward infinity because our x value is approaching 0 from the right. So 1 divided by 0 would head toward positive infinity. And, it's set as x approaches 0 from the right. And so, by rewriting the value of x in this way, we get the natural log of x divided by 1 over x. Just thought it might be nice if you, just in case you had a question about the arithmetic that was done on our way from here to here, there it is for you. And so now, what if we take the 0, direct substitution style, and plug it in? E to what power would equal 0? In other words, the natural log of 0, e to what power would equal 0? Now, instead of taking the limit of this statement, which is a rewrite, and we don't want to take the limit of this statement because as x approaches 0, e to the negative infinity would equal 0, and this is of the form positive infinity because 1 divided by 0 is infinity. So we're looking at negative infinity over positive infinity, which is the indeterminate form, which allows us to apply L'Hopital's rule. So, in applying L'Hopital's rule, we will take the derivative of the numerator and denominator. Derivative of a natural log of x is 1 over x. Derivative of x to the negative first power is negative 1 over x squared. Now can we do direct substitution? Let's plug in the 0. What's 1 divided by 0? Positive infinity. What is 1 divided by 0 squared? Oh, we're still looking at negative infinity. I don't like that. What could possibly have gone wrong? It wasn't direct substitution in this case that was going to lead us to the answer. And I know that because I just tried direct substitution with the 0 and I still got an indeterminate form. What else could I do? Go old school. This is a fraction being divided by a fraction. Keep, change, flip. So this is the limit as x approaches 0 from the positive side, 0 plus of 1 over x times x squared, well, let's call it negative x squared, or positive x squared over negative 1. Wherever the negative goes, doesn't matter. This is going to reduce, leaving us with the limit as x approaches 0 from the right of negative x over 1, which is negative x. Take a 0, drop it in there, you've got negative 0, which is 0. So even when you have the opportunity to apply L'Hopital's rule, that doesn't necessarily mean that the entirety of the subsequent process is going to be the same. In this case, we took the derivative of the numerator and denominator, and we're not then immediately able to do direct substitution. We still got an indeterminate form. When you get another indeterminate form, is it possible that the solution is to apply L'Hopital's rule again? The answer there is yes. But if there's an easier way to do it, like keep, change, flip, and reducing a couple of fractions, I'm going to pick the easier, faster, more efficient way. Also, because the chances are that there are fewer opportunities to make silly mistakes if I choose the easier path. I'm not trying to show off for anybody. I'm trying to get the right answer. Okay, I am trying to show off, but I want to show off by getting the right answer. I don't really care. As long as I'm using a legitimate method to get there, I'm going to pick the easier one. That's efficiency, not laziness. All right, now you know too much about me. In this slide, we've got a note in example 6. Another possible option would have been to write our expression in this format, so taking the product and turning it into a quotient. So the x stayed in the numerator, and then we had the reciprocal of the natural log of x pushed into the denominator. We would have ended up with this indeterminate form, but applying L'Hopital's rule, we get a considerably more complicated expression than the one that we started with. So does it matter which one of the two original factors we take and push into the denominator by taking its reciprocal? The answer should be no, because my hope is, I can't say this for sure, that it'll work out no matter which one you choose. But again, one path might be considerably easier to use or to take than another in order to get to your final answer. And I strongly encourage you to pick the path of least resistance. Here we've got indeterminate differences, so we're looking at a subtraction problem instead of a quotient or a product. And the indeterminate form might look something like infinity minus infinity. Cute, cute, cute. To find out, convert the difference into a quotient. Convert the difference into a quotient, really? So that we can end up with 0 over 0 or infinity over infinity? Is that possible? Sure is. How am I supposed to turn this subtraction problem into a quotient? Find a common denominator. And if you do find a common denominator, then you're going to end up with this problem. If you apply the limit to the numerator and denominator, if you use direct substitution, you will end up with an indeterminate form. So take the derivative of the numerator and denominator. That moves you over to this step. And here, by direct substitution, we end up with plugging in a 1 for x here. This becomes 1 over 1, which becomes 0. And in the denominator, this approaches 0. And this approaches 0. And so we end up with 1 divided by 0. We don't like that as a final answer. And so let's see what else we could do with the right-hand side of this statement. Oh, we're plugging in a value of 1, and this numerator became 0. I thought I had mistakenly plugged in a 0, and that's why we ended up with too many zeros. So a 0 in the numerator, 0 in the denominator. Don't like it. So simplifying the numerator and denominator there, we end up with this statement, copied and pasted from the previous page, or previous slide right at the bottom there. This statement is coming down here. We're working with it again. We had another indeterminate form, so we're taking the derivative of the numerator, which becomes 1. Derivative of the denominator becomes that lovely statement. We simplify, we get this. Now we attempt direct substitution, and it works, and we get a final answer of 1/2. So, moral of the story here, this is a great example of where sometimes it is the correct option to attempt the direct substitution, discover that you still have an indeterminate form, and instead of trying to finagle or maneuver or reformat your numerator and denominator after doing the L'Hopital's rule for the first time, it turns out it is the correct maneuver to apply L'Hopital's rule again. So we've talked about subtraction and products and quotients, and here we're talking about powers. And what does an indeterminate power look like? Well, here's the original format of our limit that we're working with. And if I have 0 to the power of 0, well, should it be equal to 1? Should it be equal to 0? I don't know. It's sort of a philosophical question. What about infinity to the 0? Anything to the power of 0 equals 0, equals 1? Is that true? Should that really equal 1? 2 to the 4th power is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is equal to 2. Divide by 2, divide by 2, divide by 2. Divide by 2 again. 2 to the 0th equals 2 divided by 2. Oh, it's 1. Well, anything to the 0th power must be equal to 1 then. That's an 8. It's funny. That's not really an infinity symbol. That's almost closer. Infinity to the 3rd power is infinity. Infinity to the 2nd power is infinity. How do you get from here to here? Do you really divide by infinity? I don't see that going the same way. What about infinity to the 1st power? Surely that's infinity. Can we get there by dividing by infinity again? Not convinced. As a matter of fact, infinity divided by infinity, isn't that an indeterminate form? This must not be a good method to get there. Attempting to get to infinity to the 0 equaling, Well, so far infinity divided by infinity has been infinity. I thought it was supposed to be equal to 1 because anything to the 0th power was equal to 1. But I don't like this anymore. Let's call it an indeterminate form. And finally, 1 to the power of infinity. That one you might suspect would be 1. Each of these three cases can be treated either by taking the natural logarithm or by writing the function as an exponential. How did we go from here to here? We took the natural log of both sides of the equation, so this was a y, now it's a natural log of y. And then if you slip a natural log into here, right in front of this f of x, then you can apply the power rule of the power rule of logarithms. Take the exponent, bring it out in front of the natural logarithm, and you'll have g of x times the natural log of f of x, which, look at that, that's what that says over there. This looks kind of like a bird or a turtle or something. Right, or we could write the function as an exponential. Does that really, these two, the left-hand side of this, f to the g, I see that. Really, this equals the right-hand side? How about e to the power of the natural log of f of x to the power of g of x? When you have an exponent, or you have a thing to a power, what can you do with these two powers or exponents? You can multiply them together. After they've been multiplied together, could you take it and rewrite it like this? You sure could. And what about e to the power of natural log? What do we know happens with the e in the natural log when it's formatted like this? The e and the natural log sort of cancel out, leaving you with f of x. So this would equal f of x to the g of x. Cute. Okay, so that's legit. You could write it using either of these two formats. I like knowing where those came from. That wasn't too difficult to follow. In either method, we're led to the indeterminate product g of x times the natural log of f of x, which is of the type 0 times infinity. Well, that's great, because we already know how to work with 0 times infinity. We just talked about that. That's an indeterminate product. See how we're taking one mess? We just took one mess, which was an exponential or power. Let's not call it exponential. Let's call it an indeterminate power issue. And how did we fix it? We turned it into a product issue. And how is that helpful? Because we know that we can take product issues and turn them into quotient issues. And how is that helpful? Because we can apply L'Hopital's rule to a quotient issue, or an indeterminate quotient. All right, let's see if this is scary. I'm glad somebody else worked this out for us. This is great. Let's try to evaluate this limit as x approaches 0 from the right. On the inside, applying the limit to the inner function, we get a 1. Applying the limit to the exponent, we get an infinity. So we have 1 to the infinity, which is one of the indeterminate power forms. So, right there it is, 1 to the infinity. So we need to rewrite this original equation or expression somehow. So we're going to set the argument equal to y, and then we're going to take the natural log of both sides as we did in the previous discussion. So you've got the natural log of y, you've got the natural log of your original expression. We're going to apply the power rule. The power is going to come out in front of the natural log, and we end up with this statement. What's this? Well, this is not too fancy, but the cotangent of x is the reciprocal of the tangent function, so we can drop tangent into the denominator instead of having cotan in the numerator. How is that beneficial? Well, if we now, let me just come back here. This is all one long equation, right? So we had the natural log of y was on the left-hand side. On the right-hand side, we've got this quotient. Those two statements or expressions are going to come down here, the natural log of y, and there's the quotient that we were looking at. We're going to take the limit as x approaches 0 from the right and apply it to both sides of that equation. And The right-hand side of the equation is of the form, let's see, the tangent of 0, that's 0, and the sine of 4 times 0, that's 0. So we've got the natural log of 1, which is 0. So we have 0 over 0, indeterminate form, apply L'Hopital's rule, take the derivative of the numerator, we get this, take the derivative of tangent, we get secant squared, and after performing some arithmetic, we find that 0 going into these three locations yields a final answer of 4. But be careful, because it was the limit as x approaches 0 from the right of the natural log of y that was equal to 4. We want to know what's the limit as x approaches 0 from the right of y, not the natural log of y. So how do we fix that? Or how do we conclude the process of finding the limit that we were originally asked about? We remember this fact here, and we evaluate this limit as equaling the limit applied to y. So all we're doing there is replacing this with the letter y. And why are we doing that? So that we can take the letter y, or the value of y, and rewrite it as e to the natural log of y, which makes it considerably easier for us to find our final answer of e to the 4. Why is it e to the 4? How did this natural log of y here all of a sudden become a 4? Are you telling me somehow that the limit as x approaches 0 from the right of the natural log of y is equal to 4? If you look up to the middle of the screen, I'm going to answer that question by saying yes, the limit as x approaches 0 from the right of the natural log of y is equal to 4. Absolutely. There's the left side. There's the 4 on the right-hand side. This is a problem that you're going to want to work again on your own in order to really get familiar with the details of it and see the entire process pan out for yourself. We've seen a lot of small tools in this section that are very unassuming, but they're very powerful. They're going to unlock some doors to solutions that you would not have just concocted on your own. So please take the time to become very familiar with these tools. Apply them when you're working on your homework problems, and cross your fingers that your professor lets you use a formula sheet when you take your exam on this chapter. My guess is that's not going to happen, so start memorizing earlier and check in with your professor ASAP. Okay, let's toggle over to work on a couple more example problems. The first example problem I'd like to look at is this one. Here, the limit as x approaches 5 of the quotient x squared minus 25 over x squared minus 5x. And by direct substitution, we find that the numerator and denominator both equal 0. Therefore, the conditions are satisfied for L'Hopital's rule. Next question is, should we apply L'Hopital's rule, or is there a path of least resistance or lesser resistance that will take us to our final answer, perhaps faster? I happened to notice that the limit as x approaches 5 could just as well be applied to the factored form of this quotient. In the numerator, we have a difference of squares. And in the denominator, there's a common factor of x. This allows us to cancel out the x minus 5s. This is not an indeterminate form. We can perform direct substitution here and get a final answer of 2. The next problem I'd like to look at is a little bit more involved than that one. In this problem, where we're taking the limit as x goes to infinity, if we examine this as two separate factors, you can see that this first factor is infinity to the 7th power, which is infinity. And here, this is infinity to the 6th power, but it's being negated, which is like a reciprocal. So this entire expression becomes 1 over e to the infinity. And remember that e is a number, like approximately 2.8. 2.8 to the power of infinity is infinity. So I'm going to erase the e to the infinity, and I'm going to put infinity. And what happens when you take 1 and cut it into infinitely many pieces? Each piece is very small, like 0. So now we've got infinity times 0, which is an indeterminate product. So we'd like to try to convert this into an indeterminate quotient. And we can do that very easily. In fact, we sort of just did it. Is this now in an indeterminate form that would allow us to use L'Hopital's rule or perhaps some other technique? In the numerator, we have infinity to the 7th, which is infinity. Down here, we have e to the power of infinity, essentially, which is infinity. So we have infinity over infinity, which is one of the acceptable indeterminate forms. So let's pull the trigger and use L'Hopital's rule. The derivative, well, let's rewrite the limit first. Derivative of the numerator, 7x to the 6, right? The exponent multiplies out front. Decrease the exponent by 1. And in the denominator, the derivative of e to the u is e to the u du. So we keep our original expression, e to the x to the 6, and then we multiply by the derivative of that expression, of the exponent, which is 6x to the 5. Very good. Can we simplify this fraction now? Yes, absolutely. X to the 6 and the x to the 5 are going to reduce, and that is about it. So let's see what we're left with. Okay, x is going on toward infinity, which means that in our numerator, so by direct substitution, this is going to become infinity. E to the infinity to the 6 is still equal to infinity, which means we have infinity over infinity, which is an indeterminate form. And I'm not seeing any more clever way to simmer this down into something that does not require us to apply L'Hopital's rule again. So, guess what we're going to do? We're going to apply L'Hopital's rule again. Now, as you're going through and you're taking notes on this process, don't hesitate to write yourself a note that says what we did in going from here to here was that we took L'Hopital's rule. If you need to put down some kind of a note about the fact that a negative exponent allows us to write that as the reciprocal but with a positive exponent, don't hesitate to write that kind of stuff down. If you're watching this video, the chances are you're not sitting and having to take notes on stuff from an algebra class in front of all your classmates. So there's no shame in making sure that you take notes on that stuff also in case you need that refresher. I will try to point that stuff out as I go along, but I won't dwell on it because we got to keep this ball rolling. So that being said, let's apply L'Hopital's rule again. I have no idea what just happened. I think it's going to be okay. Taking the derivative of the numerator, come on now. Derivative of the numerator and denominator again leaves us here with a numerator of 7, and the denominator is e, well, let's bring the 6 to the front first. And then we'll multiply that by the derivative of e to the x to the 6, which is e to the x to the 6, times the derivative of the exponent, which is 6x to the 5. Now let's try direct substitution again, because I don't see any simplifying that can be done. This is looking like 6 times infinity times 6 times infinity. So we're going to have 7 over 36 infinity squared, which is 7 divided by a really big number. What happens when you take 7 and you divide it by a really big number? You get 0. Fascinating. Two very nice examples. One where we were able to use an algebraic process in order to simplify the original argument so that we didn't have to apply L'Hopital's rule, even though the conditions were satisfied where we could have used it. And in the next problem, it turned out to be necessary to use L'Hopital's rule twice in order to get to a solution that for a second there didn't even look like it was a solution, like we had made a mistake, 7 divided by infinity. But don't hesitate to slow down, look at what you have in front of you, think about it for a second. It might just make more sense than you realize in an instant worth of examination. All right, now I'm starting to preach. Thank you so much for hanging with me through these couple of example problems after looking at all 30 of those slides. I appreciate you. I hope you're well. I'll see you next time.